we are mirroring. Okay, good. I think I'm good, other than I need to make this thing and not do preview mode. I don't want that.
Thanks so much for offering.
Of course, yeah. It was a good run. How the hell do you... Okay. View slideshow. Oh, there we go. Okay, good. Hello, everybody. All right. Clap once if you can hear me. I've never done that. All right, I'm stopping there. I don't know how to do two. That's too many. Actually, today's about counting, so that makes sense. So first note, I'm doing slides. I'll talk about that in a bit. Right before lecture, I realized that the slides render a little weirdly on this MacBook versus the Windows computer I was doing them on. So blame Microsoft for that. So a little bit about me. I'm Josh Hugg. I'm going to be teaching the second half of the class, which is starting after the midterm, and then I'll be on probability. But today and part of Thursday, I'm going to cover counting. It's one of those topics kind of straddles the two parts of the course, so I'm going to do this one. I'm going to do everything on slides when I teach. Sorry if you like the board. I'll give you my pros, cons. The pros of using slides is I get this very clear visual. You could see exactly what you did, but it's finite memory. But it's all there. It's very clear. I can have a bajillion slides that are slight variations on others, which is nice for showing examples for different cases. But the downside, of course, is the lecture is less alive. Although I don't have Zoom today, so I can walk around. This is good. I'm enjoying this. Okay. Anyway, so it's not the Manuel experience where it's responsive and dynamic and alive, but I will have questions for you to do. And if you've taken 61B with me, you know what that's like. I like to give you Google Forms, and that's partially because I cannot pay attention to a 45-minute talk, much less an 80-minute talk. Like, my brain just cannot do it. So if you are like me, then those questions will keep you on track. It'll give you checkpoints about what you need to do, keep things active. Hopefully you like it. I'm going to spend most of today talking about 4 counting problems, which is about half of the notes and I think about 3/5 of the contents. And then time permitting, I'll do a little bit on combinatorial proofs, but I don't think so. We'll see. So I'm going to start with the first counting problem, which is called ordered sampling without replacement. And the basic idea, and what's nice, by the way, about the second half of the course, unlike Manuel, who is saddled with this massive set of topics that are only loosely connected, is that the second half of the class is tightly connected, more so. And it's also just a little more familiar. It's not a bunch of inductive proofs, but it's the kind of things you're used to from other classes where there's like equations and you plug stuff in, you can chug through it. So it feels a little more grounded. And so I have the advantage as I'm teaching that I will have problems that are a little more concrete than Manuel, who I think had a harder battle to do. And I hear my phone making noise. Okay. So let's suppose, as a first example of this, we have 15 balls that are numbered 1 through 15, and we toss them into a bag. And then we start drawing balls from the bag. And say the first ball I draw is the 5. Then I draw a 1. And then I draw 3 more times, and I get 3, 7, 15. Okay? I've drawn a sequence of balls. That sequence was 5, 1, 3, 7, 15. And our first of our 4 problems is simply, how many total outcomes are there? So this is one outcome I could have gotten, 5, 1, 3, 7, 15. And I can actually list them out. So the first thing that could happen if we tried to come up with a natural order for these would be, I got 1, then 2, then 3, then 4, then 5. Like, lucky. Wow, what a combination. Maybe I got a 6 instead of a 5, and so forth. And I am going to be taking into account ordering. That's why this is called ordered sampling. But I can't enumerate all of these possibilities just by writing them out and counting them. Right? Does it make sense? And so, by the way, the other 3 counting problems are going to be variations. Is it unordered? Is it with or without replacement? But for now, we're going to focus on this problem. Okay? So one way to think about this is the number of possible balls that we could draw first is how many? Like, what are the choices? I say 15, and why is it 15? Because there's 15 balls, right? Could have gotten this yellow one, this blue one, this red one, and so forth. Now, after I draw that ball, how many choices are left? So I draw the 1, let's say. How many balls are left? 14, right? And so the total number of combinations that I could get from my first 2 draws would be 15 times 14. So if you draw just 2 balls from the bag, there'd be 15 times 14 options. But if I draw 3 additional balls, well, then there's going to be only 13 possibilities, then 12, then 11. And this is an example of it not rendering right on the Mac. And then the total number of possible outcomes is just the product of those numbers. 15 times 14 times 13 times 12 times 11, or 360,360. It's a nice number. So that's the number. If I were to draw 5 pool balls out of this bag of 15 balls here, and I tried to figure out how many different sequences, this is how many sequences. Okay. Let's generalize a little. Now I'm going to note that I could rewrite that as a nicer formula, and we'll see this formula shortly. This is just 15 factorial divided by 10 factorial. Why is that? Well, because if you write 15 factorial, you have 15 all the way down to 1 as your product, and then you want to get rid of those 1 through 10 factors. So I divide by 10 factorial, and then I'm just left with 15 times 14 times 13 times 12 times 11. Okay? This gives us the first rule of counting from the notes, which is if I'm building an object, okay, like some collection of things, and I build it from k consecutive choices, where there's n sub 1 ways of making the first choice, n sub 2 for the second choice, all the way up to n sub k for the final choice, then the number of distinct objects or combinations is going to be in the product of n sub I, like the product for all of the i's from I to k. Okay? We could think about it, I don't know, I picked a sort of nerdy, I don't know, Dungeons and Dragons-y type thing, which is imagine you have 3 choices that are, in this case, totally independent from each other. I could be an orc or a human, and then once I pick orc or human, then I will pick good or evil. And then after I do that, I will pick if I'm mage, thief, or fighter. The total number of possibilities is 12. That's how many leaves we get. Who here has made such a character before? Okay, there's my nerds. What's up? Who's never made a character with this kind of vibe to it? Okay, not my nerds, but you can learn. I haven't played these games much in my life in modern times, but when I was a teenager, let me tell you, I was game mastering Shadowrun. It was all kinds of stuff. Anyway, I will show you the tree for the case with the pool balls real quick. Advanced threat protection. Nope, that's just my own website. It's okay. So this is the entire tree, and maybe I'll make it a little moodier for a moment. In fact, maybe we should do that anyway. You don't need lights on the screen. That's better. Okay, now you can see. So what this thing here is it's showing you, I start at the root, and then I make a choice. I could have chosen 8, for example, and then I pick something else. And what I have at the bottom here, this little visualization that I co-created with ChatGPT-5, I'll do that a lot. So Claude Code, ChatGPT-5. I'm going to show you lots of demos that I don't like to write myself. But here, for example, one of the outcomes is, if you look closely here, it's 8, 9, 1, 5, 11. And the way I got to that outcome is first I picked 8, then 9, then 1, then 5, then 11. And it's a really big tree, right? Like, it would take you a long time to scroll through this whole thing. But that's all the possibilities. And how many leaf nodes are there, do you think? Do you remember? 360,360. So there they all are. And when you're done with class, you can count them manually if you want to double check. Okay? So there's lots of room. Okay, but there's also the answer there if you want. That was a nice little feature that GPT-5 picked for us. Okay? All right, any questions so far? I'm just kind of ripping through. Yeah?
Sorry, you mentioned when you did the factorial,
yeah.
by 10 factorial. Can you explain that again?
Sure, yes. So this is where it'd be nice to have the board. The reason is, imagine that you had, if you wrote out 15 factorial, you'd have 15 times 14 times 13 all the way down, I should get a pen or something, all the way down to 1. And in the denominator, you would have 10 times 9 times 8 times 7 and all the way down to 1. So the 10s would cancel out, the 9s would cancel out, the 8s would cancel out. And what would you be left with in the numerator? 14, 13, 12, 11. Yeah, does that make sense?
Well, why do you do that?
Oh, this is just another way I could write it. Like if you don't like this, and I'll show the other form. If this feels like a little, I don't know, not nice, this is just another way you could write it. These are equivalent expressions.
Oh, so you're just trying to draw the first 5 balls.
Yep, just drawing the first 5 balls. I could write out 360,360 either as this number, 15 times 14 times 13 times 12 times 11, or I could write it as 15 factorial over 10 factorial. That's all. Yeah. Any other questions? Okay. All right. So let's generalize a little. Let's say instead of drawing 5 balls from 15 possibilities, let's draw k balls from n possibilities. So the total number of outcomes, if we just pattern match, is going to be n times n minus 1 times n minus 2, all the way down to n minus k plus 1. Now, why is it n minus k plus 1? Well, I'm just pattern matching, right? I'm going to go down to 15 minus 5, 10. Oh, 10's not right. I need to add one more. That's basically the idea there. Okay, so I'm just going to pattern match off this and say I'm going to multiply it starting at 15 down to n minus k plus 1. So you could write it this way, the number of total outcomes this set A, you can think of A, by the way, as the set of all possible sequences, and this notation here is saying the number of items in the set, right, the cardinality of the set. And so this set right here, we end up with 15 times 14 down to 11, which we could also rewrite earlier, I mentioned, as n factorial over n minus k factorial. Okay? So both of those expressions are perfectly reasonable. This one's a little more compact, obviously, than this one up here. Like, this just feels more natural. Though this is a perfectly reasonable thing to write out with mathematical symbols. People will know what you mean, even if it is a little clumsy. Okay? All right. Any questions about this? So all I've done is just generalize the pattern. Another way of thinking about this is I just use the first rule of counting again. I started with n things. Then I only had n minus 1 things. Then n minus 2, all the way down to n minus k plus 1. Okay? So this problem is also known as ordered sampling without replacement. The reason is each ball you draw is a sample, and the entire sequence I'm calling an outcome today. Ordered means we care about the order, so 1, 2, 3, 4, 5 is different than 5, 4, 3, 2, 1. And without replacement just means we don't put the balls back between samples, so we couldn't get 5, 1, 5, 6, 3, because we don't put 5 back in the bag. Okay? All right. Let's talk about another problem that is related, but a little different. Some of you may already know this, but let's say we have, let's do another counting problem that's not CP1, at least not obviously. Let's suppose we have 5 letters, A, B, C, D, E, and A is the set of all permutations. So A is A, B, C, D, E, A, B, C, E, D, and so forth, all the way up to E, D, C, B, A. How many different permutations exist? What is the size of that set? Okay. So I'm going to let you think about this for a second. If you do know it and if you don't know it, try and think about how is this related to counting problem 1? How can you solve this? There's 2 different ways you could solve this, basically. One is using the first rule of counting, and the other is just using that formula for CP1, which I guess I could write on the board. Maybe I will. Okay, I'll let you think for a sec. Okay, I'm going to steal back the room on this one. So someone give me a quick, what's the answer? First of all, yeah? 120, great. So how do we get that? That's 5 factorial. Why is it 5 factorial? Someone give me an argument in terms of the first rule of counting? Nobody? Yeah?
Because we're making a sequence.
Yeah?
Start with 5 choices, then you take 1, then you have 4 choices.
Right. So first you take the first letter, let's say it's A, then you draw the next one, maybe that's B, you draw the third one, that's D, and each one of those draws you have 1 fewer. So it's 5 times 4 times 3 times 2 times 1, directly from the first rule of counting. How can we use the formula for this counting problem 1? What's n and k in that case? Yeah?
N would be 5, and then k would also.
Yeah, n is 5, k is 5. So it's a special case where n equals k. So using our general formula, oops, I'm missing a exclamation point there, sorry. That would be 5 factorial over 5 minus 5 factorial. 5 factorial over 0 factorial gives you just 5 factorial. Why is that? What's 0 factorial? 1, okay? You might not remember that, but it is a fact. There's many different arguments for why that's the sensible definition. This is one of them. And that gives you 120, okay? So the number of permutations is a special case of counting problem 1, where the number of draws is identical to the number of items. Any questions about this? Okay. Out of curiosity, how many people remember that the number of permutations was in factorial, but did not remember how to derive it? Anybody? Some? Okay, got some hand waves. All right, good. Okay, let's talk about ordered sampling with replacement. This is a different problem. This is the problem where I can get repeats. That's it. That's the only thing. It's different. So in this case, I could draw the ball 1 5 times in a row. We still care about the order. So 1 1 1 1 2 is different than 2 1 1 1 1. And so I want to know how many outcomes are there. Okay. So the key difference is that we're putting the ball back each time. And in this particular case, this one's actually really easy if we've already done the first problem. We could just use the first rule of counting again. And in this case, the draws are totally independent. So the first time I draw, I have 15 choices. Then I draw again, I have 15 choices again. And so what's the answer going to be in terms of the total number of possible draws or outcomes? 15 times 15 times 15 times 15 times 15, or 15 to the fifth. So now I have 759,375 outcomes. The end. There's not much more to that. And there they are. I listed them all. Okay, good. Okay. And so the size of the set, where we consider the set is the number of, the set is all sequences that can have repeats, where we do care about the order. For 15 items and 5 draws is 15 to the fifth. And in this case, we call it sampling with replacement because the balls can go back in the bag. That's all. That's a short one if you got the first one. Okay? Let's do something harder and more interesting. Okay? Let's talk about unordered sampling without replacement. So now we're going to discuss unordered sampling. We're going to stretch our brains a little more. In this case, we're going to consider 2 outcomes the same if they're just permutations of each other. So let's suppose we place the letters A, B, C, and D in a bag, and we draw 3 in a row. And let's assume we do not put the letters back, so it's without replacement. So for example, maybe I draw B, D, and A, and I'm going to use set notation to indicate we don't really care about the order. There should be no duplicates. I mean, obviously, there can't be duplicates because we were not replacing, but it's also a set, right? So this is a set. We have B and D and A. We don't care about the order. So now the question is, say we don't care about the order. Okay, we treat BDA the same as ABD. How many different ways are there to draw 3 letters? Okay, so to solve this, one approach is, this is very typical for counting problem 3, is we'll first temporarily pretend that order matters. Because we already know how to solve that problem, right? We know how to count sequences where order matters. So we'll consider counting problem 1, and then we're going to group together permutations and say, well, you don't count, right? You things are all the same. ABC is the same as CBA. So we're going to lump those all together and ignore the fact that there are actually multiple of them. In fact, we're going to squeeze out, we're going to give just like one representative from each of these permutations, and we'll only count that one. The idea. So I'll do this exhaustively first just to show you the lazy way of doing this, which is, imagine I have all of the ordered outcomes, so I picked some arbitrary natural ordering. Here they are. There's a bunch of them. And you could use counting problem 1 to count exactly how many, or you can count commas, I guess. Then what I'm going to do is I'm going to look for all of the outcomes that are really the same in disguise. So give me an example of 2 that are the same but in disguise. Well, I already have one on the slide, BDA and ABD. Here I have ABC. Here I have ACB and so forth. So all of these permutations of just the letters A, B, and C, I'm going to color those red. Oops, okay. I guess I had more stuff I wanted to say. Hey, there's 24 of them because of counting problem 1. I forgot. Okay, so I'm going to group these together, and I got all these ABCs together. They're red. Okay. How about ABD? One other example is ADB. Another is BAD, and I'll put those in blue. I'll also have these in green, and I'm left with just 4 different colors. If you're red-green colorblind, sorry, but hopefully you have enough color vision that you can see that there are multiple different colors. Now what I'm going to do is sort by color. So I'm going to bring all the reds together, all the blues together, all the greens, and all of these black items together. And I'm left with these 4 colors. Okay? So the basic approach was, first I found all the outcomes. Then I said, oh, well, there's really only these red, blue, green, and black colors. And so question for you. If B is the set of unordered outcomes, okay, like we do not care about the order, what is the size of B? Ooh, and this didn't render quite nicely, but that's okay. So you can answer this at this URL, and hopefully it works. Let's find out. So B is the set of all sets. match this pattern. Oops. And if you don't have a QR code reading thing, you can just use this URL. But the internet's not working on my phone. Troubling. Okay. I'm going to give you slightly longer while I get my phone connected. Okay. Really, I wish I had your answers. Okay, C3 equals 4. All right, cool. Okay, here we go. Okay, so we are 90% correct that the answer is 4, and that is indeed the case. There are only 4 different possibilities. You could have drawn a combination of A's, B's, and C's, red. You could have drawn a combination of A, B's, and D's, blue, A, C's, and D's, green, or B, C's, and D's, black. Okay? And those are the only possibilities. So there's 4, 1 for each color. Okay? All right. So that brings us to the second rule of counting. Okay? So when we ignore order, we have a different rule, which is, and this is straight from the notes, which is assume we have an outcome, we have a succession of choices, and the order in which they're made does not matter. One way to fix this, or one way to solve this problem, is say that A is the set of ordered objects. You pretend for a moment that you do care about the order. And let's say B is the set of unordered objects, the actual thing we care about, right? Just like we did with the number of draws ignoring order. If we have an m-to-1 function f that maps A to B, then the size of the set B is just the size of the set A divided by m. So in other words, when I put A in braces like that, that's the size, or between bars, that's the size of the set that where we're temporarily pretending to care about the order. And then what we actually want is the size of the set, ignoring order. Okay? So you should be thinking, wait, what? When did we create an m-to-1 function? Like that sounds like, notes madness, where I got to spend all this time unpacking what's going on. So question for you, when do we create an m-to-1 function? I'll let you think about that for 30 seconds or so, and I'll solicit an answer. So the set A has 24 items in it, which are ordered sequences. The set B has 4 items in it, which are sets. Okay, so what's the function? What's m? 6. M is 6. So we have an m-to-1 function that takes exactly 6 items from set A and maps them onto set B. So that function would take these sequences and map them to the set containing A, B, and C. Okay? So we were able to construct such a function. Therefore, we have that this size of the set that we are mapping onto is going to be 24 divided by 6. Okay? That's my answer. I don't know. I didn't solicit an answer from you. I'm getting back in the CS70 groove. I forgot I made that slide this morning. So basically what we did is we just grouped the permutations together into bins, right? Or colors. The notes uses the term bins. And each bin consists of exactly the 3 factorial equals 6 permutations. We already know that the number of permutations is just 3 factorial. So that's why we ended up with 6, because we were dealing with collections of 3 things. So we end up with 24 items divided by 6 items per bin, leaving us with 4 total 4 different outcomes. Yeah. Yes, in this particular case, it will be k factorial. Right? I'm sorry, not in CP3, it will be k factorial. Indeed. Okay. So, drawing on that, I'm going to give you a slightly different version of the problem, which is say we have 26 letters, A through Z, and we draw k equals 5. And B is the set of unordered outcomes. That is, it's a set of sets. One of the sets is the set containing A, B, C, D, and E. Another is the set containing A, B, C, D, and F. How many total sets are there in that set? In other words, what is the size of that set? So first, I want you to tell me, let's do it in 2 steps. What is the size of the set A? Remember that that set is the set of ordered outcomes. We're going to pretend temporarily that we care about order. Okay, I'm waiting for more answers, so I'm just going to wait until I get about 100, which is about how many I had before. Okay. So there are 2 correct answers. One of the correct answers was 26 times 25 times 24 times 23 times 22. The other one was 26 factorial over 21 factorial. And that second answer was a little more popular. So you guys tended to like to pick this one. So there's 7,893,600 different draws you could do if you took into account order. Okay, next question for you, which is the natural question, drawing off of what the student asked earlier, is, well, then what's the size of B? What's the number of sets? If we ignore the order. Is that the same question again? No. Okay, good. Okay, this time we're around 75% correct. Okay, so there's 7,893,600 different ordered combinations. And how many permutations are there for any particular sequence we have here? 5 factorial. So what we know is that the number of permutations for bin is 5 factorial. So the answer is just going to be that size counting all the sequences and then saying, well, there's 120 different sequences that correspond to each element of the set of sets. So I'm going to divide by 120, and I end up with 65,780. Any questions about that? Okay, so this is a direct analogy to what we did before. It's just that in this particular case, there's 7,893,000 different little strings, and there's how many different colors? 120 colors, yeah. Okay. Or no, sorry, that's not correct. How many different colors? 65,780 colors, each of which has 120 strings in it. Okay? All right. So this number is so important, this quantity, that there's a special name and notation for it that you've probably seen at some point in the past. So this number is known as 26 choose 5, or in this special notation, you just do parentheses and put 26 over the 5 in the parentheses. And this expression here, if I zoom in a little bit, this right here is our choose function. It says that, so the answer to this question, if I have 26 items and I draw 5, without replacement, and we don't care about order, is in choose k. Now you'll notice here that it's just counting problem 1. So counting problem 1 was n factorial over n minus k factorial. That's the number of sequences, number of different draws if I take into account order. And then what I do in order to get to counting problem 3 is I lump all the permutations together. How many permutations were there? If I have 5 items, it's 120, or k factorial in general. So I'm taking my counting problem 1 and dividing by the number of permutations. That's my m to 1 mapping. Okay? So for example, if I'm doing 26 choose 5, first I compute the number of different sequences where I care about order, and then I divide by the number of permutations there are per bin. Okay, any questions about this? Yeah.
So this is specifically for the problem 3.
Problem 3, right, yes. So unordered sampling without replacement. Okay. You've seen this choose quantity. It appears in other cases, like for example in the binomial theorem, which maybe we'll get to at the end of the lecture today. But this is a nice definition or source for where this function comes from in the first place. Okay. You can think about this as the number of ordered outcomes, and this right here is the number of outcomes per bin. So if we were to, a number of ordered outcomes per bin. So we divide the number of ordered outcomes by number of ordered outcomes per bin, I'm left with the number of unordered outcomes. Okay. All right. So if I summarize my counting problem so far, what I have is that counting problem 1, which was ordered sampling without replacement, this was this formula, n factorial over n minus k factorial. That came from our first rule for counting, which is we're simply saying I started with n choices, then I had n minus 1, and so forth. This was the really simple and straightforward one, which is all my choices are independent, so it's just n to the k. Then I have this problem, which is in counting problem 3, we first count the number of outcomes, imagining temporarily that we care about order, and then we lump things in together by bin, which in this case is k factorial. So that leaves us with one more natural counting problem, which is, what do you think? If you had to name it, what would you name it? Unordered sampling with replacement. There you go. That's what we're going to do. Great. Okay, so let's suppose we have 3 balls with the letters X through Z on them. And then we draw 5 in a row, and we put the ball we drew back in the bag each time. So maybe the first draw I get X, then X, then X, then X, then X. Then I have X, then X, then X, then X, then Y. Okay. Maybe the next time I get X, then X, then Y, then Y, then Z. Those will all be different outcomes. Now in this particular case, these right here, these are multi-sets. They allow duplicates, but the order doesn't matter. Okay, so there happen to be multiple X's in there, that's fine, and we don't care about the order. I'm going to call this counting problem 4, where there are n equal to 3 choices, and we did k equal to 5 draws, and naturally the question is, well, how many of these occur? Okay. Now I should do a quick note, just a quick aside, that I could have represented, ooh, it looks ugly. Okay, this time I'm actually going to fix it. This is a rendering error that makes me too upset. Okay, you get it to be whiter now. Okay, good. All right. So here, now we got to turn this off. Slideshow. Okay. All right. So here, I could also have written this as 5 X's, or 4 X's and 1 Y, or 2 X's, 2 Y's, and 1 Z, instead of using the set notation. Right? So that's the set notation version. This is another way you could write it. And that would be perfectly fine, but I'm going to stick with the multi-set notation. But if in your head it's easier for you to think, oh, it's really just the numbers that counts, that's fine. To avoid confusion, I'm always going to list the multi-set components in alphabetical order. So I will write X, X, Y, Y, Z rather than X, Y, X, Y, Z, because, I mean, even though technically those are the same multi-set, I just want a canonical representation of a particular multi-set. By the way, canonical representation is a very nice idea in mathematics, which is the notion that you want to have like one actual name for a thing. And so I think a nice name for this multi-set is X, X, Y, Y, Z, and we won't allow these other ones for the rest of lecture. Okay. So we'll define B this time as the set of all possible outcomes. In other words, it's the set of all multi-sets, okay, that with this, for this problem setup. Okay, not all multi-sets that could ever be, but it's a set of all multi-sets which are a collection of X's, Y's, and Z's that is length 5. Okay. So counting problem 4 is the question of how big is that set? That's what we're going to try and do. So question about counting problem 4 is just how many multisets exist if n equals 3, k equals 5. And so let's suppose we tried to use the second rule of counting, right? So remember the second rule of counting, the way we did that is we first found the size counting order, which in this case would be 3 to the 5th or 243, because I have to make, I have 3 choices and I pick 5 times, so I get 243. And then I try to find an m to 1 function. Turns out that's actually not going to work here, and let's see why. So question for you, the next little question here is how many ordered outcomes are in the same bin corresponding to this? So if I temporarily take into account order, how many different outcomes will be in the same bin as the ordered sequence XXXX? And how many ordered outcomes are in the bin corresponding to XXXXY? It's a little bit fuzzy of a question, but I hope that it makes sense. I could have been a little more precise in my framing, sorry. This one you have to type, so maybe you're less into it. Yeah. Oh, I see. It wasn't HTTPS. I see. Okay. How many of you got sent to some Indian restaurant Google search result? Okay, got it. Okay. I didn't put the HTTPS, I guess, in the QR code, so there it goes. So you were actually just Google searching for josh.ug/d. But please go. What is it? Where is that restaurant? Is it in Berkeley?
Shattuck, yeah.
On Shattuck. Okay. So I get $1 each time you eat there. So please eat there, and I will enjoy my fortune. Okay. So the answer is there's only one sequence in. This is a little sloppy. Sorry. In terms of being precise mathematical notation here, but there's just one outcome that matches XXXXX. And then in the case of how many different sequences are there that have 4 X's and 1 Y? There's 5 of them, okay? In other words, if we tried to do the color trick, it's not going to work because there isn't the same number of things per bin, right? Some bins will have 1 item, some will have 5, and so forth. There will not exist a simple m to 1 mapping that will make our lives easy, okay? So ideally, if we just wanted to use counting problem, or the second rule of counting, we would find the number of outcomes taking into account order, and then we'd find an m to 1 function, but there is no obvious m to 1 function that we can use to lump into outcomes, so we need to be a little more clever. So there's a lot of different approaches, but our main goal, and this is going to be maybe the most important thought of the day, which is that we want to map our problem into some other domain we can more easily analyze, right? One of the most important things for me in grad school, and to some degree as an undergrad, was the ability to recognize that this problem is really just that problem. In fact, I would argue that if you're learning computer science or data science or mathematics, that's a lot of what your training is. It's recognizing that a thing is really another thing in disguise. Incredibly important. And so what I'm going to do here is imagine a new construct, which is just a little easier for me to walk my way through. This is not in the notes. It's a little bit weird. But I want to give an example of how one might construct such a mapping. So one approach is imagine we have 3 different, sliders that go from 0 to 5, and they're going to represent how many x's, y's, and z's we have. So for example, the multiset x, 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 y, I could represent by these 3 sliders. I set x to 4, y to 1, and I set z to 0. Okay? Or I could do, for example, x, x, y, y, z. I mean, really, that's just 2 x's, 2 y's, and a z. Okay? Why do you do the slider? I don't know. It's just like a nice picture. And it's going to be nice because I'm going to try and count how many different valid slider positions there are. That's what I'm going to do to make my life easier. Any questions about this slider thing? So it's just another representation. So which of the settings below is valid? Here's 2 of them, okay, for this problem. Okay. Anybody want to throw out an answer? Is one of these good and one bad? What do you think? Yeah?
I guess both of them are valid depending on what the multi-set you're
True, but I wanted to map to this problem at the top. So yes, both of them could be valid multisets, but what about for this example here where we have 3 balls and we're drawing 5, yeah? The right one seems good because we have 3 x's, 1 y, and 1 z. This one's not so good because we have 2 x's and 1 y. We haven't drawn all 5 balls. So that one's no good, that one's good. Good? There's some muttering. Now I'm nervous. No, okay, should be good. So this is a valid setting. I could set the sliders like this and it won't explode. Okay, that's good. Okay, so then what if A is the set of all valid slider positions, right? For example, here's one of the representatives. What would be the size of the set A? Remember, our 3 sliders have to sum to 1, so I can work this out without too much trouble. If I gave you time to do it, you could probably do it without too much time, but I'm just going to give this one away for free, which is, I'm going to kind of walk through it. If x were 0, for example, that's one of the choices. How many valid positions are there such that x is 0? Oh, maybe I should have given this one to you on Google Slides. So when I say valid positions, I mean, I guess you can call them settings. Yeah. 5. I got 5. Anybody disagree? 6. Who says 5? You. Busted. Yeah. You have some confidence to you, though, so I know you can take the heat. Who says 6? Okay. Who says 38? Just trying to bust somebody again. Anyway, all right. So 6 is indeed the answer. We could have, for example, that y is 0, z is 5. We could have y is 1, z is 4, and so forth. So whatever y you select, what's z going to be? 5 minus y. Okay, so there's going to be 6 positions. Okay, great. Let's say x is, so if y is, oh yeah, sorry. This is just some examples, right? Okay. So if x is 0, then these are all the combination of y's and z's on the slide. Okay. Let's say x were 1. How many valid positions are there for y and z? Okay, hold on. I gotta make eye contact. So if x is 1, how many positions are there for y and z? Yes! There we go. Yeah, I'm with you. So there's 5 because y and z have to sum to 4. Okay, I knew there would be at least one mistake today, sorry. Not battle-tested slides. Scary. That's the other downside of slides, is that when you make an error with the board, you're just like, oops, erase. But I have to make the screen smaller and then delete and then do something. It's more embarrassing. All right. If x is 5, how many valid positions are there? 1. There's actually 1, not 0. Okay. There's only one choice. So the total number of valid positions would just be working through all those cases. If x is 0, there's 6 things that y and z could be. If x is 1, there's 5 things that y and z could be. If x were 5, there's only 1 thing that y and z could be. Okay? If x is 6, well, then you're in trouble. Nothing works. We don't allow negative sliders in this world. Okay? So the total number of valid positions here is 21. Any questions about this? Yeah. Isn't this a bit genius? Are you just glazing me? 'Cause I was, yeah. I guess it is. It is genius. Anyway, all right. So what we've just shown is, I hope I used that word right. What have we just shown is a more fundamental, okay, backing up. What we've just shown is a more fundamental rule for counting, which the notes called the 0th rule for counting, but I call it the ultimate rule for counting because it sounds bigger instead of nothinger. So the rule here is that if I have 2 sets A and B, and I can place them in one-to-one correspondence, that is, map every item in A to exactly one item in B, and vice versa, also called a bijection, then we know those 2 sets are the same size. So what we did was, okay, well, we had this like multi-set question about drawing balls. Let's turn it into sliders instead and count. Okay? So A was the set of all multi-sets for n equals 3, m equals 5. And that was equivalent to the set B, which is the number, or the set of all slider positions with settings 0 to 5, where the sliders have to sum to 5. Okay? When I do that, I was able to reason about B with some nice pictures, and I ended up with 21. All right. Now this bijection is a bit unwieldy, because if you try to add more sliders, if you increase n, it gets hard to compute the sum. I mean, you can still do it, but it's just a little awkward. So instead, I'm going to show you the even nicer and actually genius bijection that comes from the notes. Okay? So another approach, and this is just, again, out of nowhere. This reminds me, many years ago, before John De Niro and I had kids, we sat in on the real analysis class. We don't have children together. Because if we did, what size? Hold on. All right. Weird. We have to call John really quickly. Hold on. It's important. Okay, hold on. See if he answers. Hello? Oh, hold on. I don't know if I have a signal. Oh, that's sad. I have 2 kids. John has 1 kid. A bijection? No. So if John and I had kids, though, what size would they be? That's a very interesting question. Guess they'd be a regular sized guy. Anyway, all right. I know one person who's much taller than John De Niro, who was our landlord in the Netherlands. He was 6'9". It's pretty wild. Anyway. Who's the tallest person here? Oh, it's John. Hello. Can you hear me? This is a bummer. Hey, I'm teaching a CS70 lecture, and I thought it would be funny to tell you what just happened. So I was going to tell a story about when we went to real analysis class, and I said, before John De Niro and I had kids, and then there was an awkward pause, and then everyone laughed, and then there was applause, like riotous applause, and now we've been talking about this for a full minute. All right, anyway, just how you should know. All right, bye. All right, bye. John laughed and said, enjoy your lecture. Okay. Anyway, we sat in on a real analysis class before we had kids separately. And I remember the professor, she was like, did something on the board and then said, why did I decide to do that? And she said, because it works. I don't know. You get practice, and then you can see that this is the right thing to do because it works. So this is one of those, right? It's like, where did this idea come from? Someone clever at some point. Often math problems are much easier to understand the solution of than to create a solution. This is an interesting asymmetry in the way that we deal with mathematical objects. Proofs can seem obvious to you once you've seen the solution, but until you see that step, you might spend days until you realize the one little subtle thing. So this is one such really beautiful idea that makes this problem nice. So what we could do is represent each multiset as a binary string. And what's that multiset or the binary string gonna look like? We're gonna have zeros representing x's, y's, and z's, and ones acting as a separator for each type. That is not enough information to understand it, but the examples will make it clear. One would be the multiset xx, y, z, z. For screen reasons, I've not written it out in multiset notation, but what I mean here is the multiset with 2 x's, a y, and 2 z's. And the string I'm going to have is 2 zeros. Why 2 zeros? Because that's x. X always comes first. So each x has a placeholder 0. Then we have a 1, which is a separator. Okay, weird. And then we have 0, because that's the y. And how do I know it's the y? Because I got past 1 separator. Then I have another separator, because I'm out of y's. Then I have 2 zeros for my z's. Okay, that's the idea. Let's do another one, and then I'll make you do one. Let's say I have 4 x's and a z. Well, then I'll have 4 zeros up front, then a 1, then another 1. Why did I do 2 1s in a row? Because there were no y's. And then we have a 0 for that last z. By the way, it doesn't have to be zeros and 1s. It could be stars and lines. It could be x's and y's, whatever. But I did zeros and 1s. Was that your thought? No? Okay, yeah. So I picked zeros and 1s. The fact that it's a binary string of numbers does not matter. It could be any pair of objects, hearts and triangles, whatever. Okay. So question for you, what would be the natural representation for x, x, y, y, z? This is just a are you following the slide type question, but I do want you to think about it. And let's see if this one is correct on the URL, or is it a Google search again? Oh, it worked, okay. Okay. Just a few more. Oh, I ran out of minutes on my phone. Okay, I have to disable my blocking app. All right, so the correct answer was 001010, and I will be disabling my blocking app. I give myself 20 minutes of phone time a day, but I ran out because the phone is bad. All right, good. Okay. Does it make sense? Any questions about what this representation is all about? Okay, so then let's let A be the set of all such valid binary strings. We want to know what's the size of A, naturally. Okay, so what is the size of A? Well, question for you. Can you see how this is related to one of our previous counting problems? Just think about it for a sec. Like, what does this feel like? I'm going to give you 30 seconds, and I'm going to give you some scaffolded thinking. It's kind of related. Actually, I'm just going to interrupt you. Okay. All right. One way to think about it, and this is the part where we're going to really focus our energy. I think we're feeling motivated, okay? So we know that the ones can be in position 1, 2, 3, 4, 5, 6, or 7, right? We know the string's definitely 7 items long. You just built one, right? It's 2 separators and 5 zeros, okay? And in a sense, we can think of it in the first string, we kind of like, if we imagine it as a counting problem, we drew a 3 and a 5. And what does that 3 and 5 means? It means I drew the positions of these ones. Here, I drew what? I think 5 and 6, yeah, right. In the third string, we drew 3 and 6, right, okay. So in some sense, each of them is a different draw from the set of all possible strings that are valid. And so what question is this? Don't talk to anybody. I want you to answer on your own for a sec. See if you can figure out, is this CP1, CP2, or CP3? And then I'm going to have you talk to your neighbor. I'm doing one of those. I haven't done one of those in a while. So if you're wrong, that's fine. Don't talk, though. I don't even know who you are. I don't collect email addresses for this thing, so. You have to sit in awkward silence. And I think this is a really important question because it's the kind of reasoning you will need to be doing in this class. Okay, I'm waiting for 40 more answers. No, they're coming in fast now. All right, good. Okay, so what counting problem is this? Talk to your neighbor, and I'll have you resubmit when you've had a chance to think about it. So talk for a second, then I'll give you another link. Okay, try and convince your neighbor of your answer. You get 2 minutes, though. Really talk about it. Oh, I see. All right, you can answer again if you want now. Wait, uh-oh. Should be a letter G up there, by the way. The QR is right. But if you're typing in the URL manually for some reason, make sure you put the letter G. This is interesting. Okay, I'm going to wait till there's 125 responses. So go wait. You should both answer. If you and your... So if you talk to someone else, you should both still answer. Still waiting a bit more. Sorry, but I want to know how people do. 43%. This what? Spacer trick? Yeah, basically. I don't know by that name, but all right, fewer people wanted to answer this time, but that's okay. I accept that. So the first time you guys were 43% right. This time you were 56% right. But I'm going to stop it now because I don't want the answers. I want the real deal. Okay, stop collecting. Okay, I can't stop it apparently. Well, that's unfortunate. Hold on. I want to turn it off because I want to look at this data later. If you keep firing them off, though, that's fine. One sec. Why won't you let me stop? Okay, so it goes. I'll just remember. Okay, so it turns out that this is unordered without replacement. Okay, that's kind of surprising. So about 56% of you had that right. So let me justify that for you because it's pretty interesting. Like, it's not obvious to me, like, you know, at first glance, unless I think very carefully what the answer is. So why is it unordered without replacement? So basically, it is counting problem 3, where n is 7 and m is 2. Okay, we're drawing two things. Wow. All right, so we're drawing two things. And what are those two things we're drawing? Let's try that again. We're drawing the positions of our ones. Okay, so there's the first thing we draw, maybe we draw a 3. That's the first position for a 1. And the next thing I draw is a 5. Okay, so the different draws I could have made are 1, 2, 3, 4, 5, 6, or 7. So the first draw I make is a 3. The second draw I make is a 5. Okay, does that make sense? Okay. Now, does it matter if I drew the 3 first or the 5 first? No. That's why it's unordered sampling. And why is there no replacement? Like, describe it to me in a word. Like, why is it unordered? Or so why is it without replacement?
Because if we already drew position 3
Yeah.
for one of the ones, we can't put another one in that same position.
Right. We can't put another one in that position. Right? We cannot have two separators that overlap. Okay. So we had 7 different positions where the separator can go. We drew the first separator. We drew the second separator. Okay. Sorry. Let's delete that 1.5 minutes where I was saying total nonsense, which is the exact opposite of what I should have been saying. Okay. So it makes sense. We're drawing the 2 positions for our ones. Okay. All right. Any questions about this? Yeah. So if it were not binary, then it wouldn't be our original problem anymore. So you're basically saying, oh, what if there were more things, 3 things I could draw that would not correspond to the multi-set counting problem anymore? So now you're doing a different counting problem entirely. Yeah. So this little subproblem we're doing here, this counting problem 3, it's saying that the original goal of how many different multisets are there is the same thing as these number of binary strings. And how many binary strings are there? Well, we imagine, okay, so it's linked 7, and we need to draw 2 separator positions. Okay. So in other words, the number of different places the separators can go is the number of different multisets. Okay. Happy with that? Okay, so that's why we had 21. Because there's 7, another way to think about this, just in terms of 7 choose 2, how many different places are there for the first separator? 7, and how many places are there for the second separator? 6. Okay, so we got 21. Okay. All right, let's generalize a little. So there's an interesting thing we can do is that we can observe that anytime we're doing counting problem 4, it's really just counting problem 3 in disguise. Okay, so let's pick a different combination. The way I think about it is, if I pick an n and a k for counting problem 4, you can find an m prime and a k prime that I could just feed to counting problem 3, and it'll give me the answer. Okay? So for example, let's suppose we do n equals 4 and k equals 7. So what that corresponds to is I'm drawing 7 letters from a bag of 4 possibilities, w's, x, y's, and z's. Okay? So if I want to think about that in terms of counting problem 3, in terms of separators, what are n prime and k prime going to be? Try and think about that for a sec. So we're thinking about this in terms of separators. I guess question for this problem, how many separators will there be? 3, okay, right? How long will the string be? 10, right. Okay, well, I guess I told you that one already. Okay. Sorry, I forgot I had a Yelke or a Google question. I'll let you think about it for a sec. You don't have to answer this one because I already said the answer out loud. Will I give you a second to reflect? Okay, so k prime is the number of separators. N prime is the number of digits. So it's going to be 10 and 3 this time. So let me just repeat that. If I draw 7 letters from a bag of 4 possibilities, you have 3 separators, and the string is going to be linked 10. What are the other 7? So there's 3 separators and 7 whats? 7 zeros, which corresponds to each of my draws. So for example, on that bottom one, there's 1 0 corresponding to the W, there's 3 zeros corresponding to those Y's, and there's 3 zeros corresponding to those Z's, right? Oh, here they are. That's the string. Okay. All right, happy with that? So draw 7 balls from 4, draw 7 letters from a pool of 4. You get, that's the same thing as saying how many strings are there of length 10 with 3 1s in them. Okay? And then we could generalize even further. Let's just say in general for n and k, what's that going to be? There's no thing to submit here because it's too hard to type out. But I'll give you again a minute and a half or so to think about this. So if we're drawing k items from a collection of n things, how many separators are there and what's the total length of the string? Think about that for a minute. Oops. Okay. So if we have n different letters, how many separators will we have? N minus 1. So in other words, the number of separators is always going to be, k prime will always be n minus 1. And then how many digits will there be? You could be off by 1 if you want. N plus k minus 1, right? So the way I think about it is, yes, the number of separators is always n minus 1, right? That makes sense. If I have w, x, y, and z, I need 4 minus 1 separators. That's 3. And then how about over here? The number of total digits is the separators, n plus 1, or n minus 1, plus k. K is how many things, how many letters I'm drawing. Now, one thing that could be a little tricky to wrap your mind around is it feels weird that I'm like k equals n. Like n and k feel like the opposites in some sense, but that's because we're moving from counting problem 4, in which n and k have a certain meaning, and we're moving to counting problem 3 where they have a slightly different meaning, right? So that's why it seems a little weird, but if you want to follow just the argument literally as I'm going, and you'll have time to reflect more after, it's thinking about this. K prime is the number of separators, n prime is the number of digits, where we have n minus 1 separators, and then we have k digits that are zeros, the things that we are representing each of my w's, x's, y's, and z's. Okay? All right. This is where I think your brain is hitting sort of the part where it's stretching a lot. So again, please revisit this after the lecture. Like, make sure this formula makes sense. That's the mapping from counting problem 4 to counting problem 3. Okay? So summarizing maybe at a high level what's going on here. Originally, in our original problem domain, we're counting multisets, but that's hard to do. So then we imagine, okay, what we're really trying to do for counting multisets is we can imagine that we're writing strings that represent the multisets, and in that context, now I'm drawing we're doing counting problem 3, where I'm drawing the position of my separators. So drawing multisets is equivalent to drawing the position of separators from strings. And that's the whole story. That's how we get from counting problem 4 to counting problem 3, is transforming it into the question of just drawing the separators. Okay. So if we were to summarize those 4 different problems, what we found is that counting problem 4 really is just counting problem 3 in disguise, right? So if I'm trying to collect letters from I'm drawing different letters from a ball, drawing different letters from a bag of letters, that's really the same thing as drawing separators. That's what I'm saying here. And the way I map from n and k and CP4 land to n and k and CP3 land are those expressions that you just derived. So if I just literally plug this into the n choose k function, I end up with k plus n minus 1, choose n minus 1. In other words, you have a string of k plus n minus 1 things, and you want to choose the n minus 1 separators. Okay? All right. Questions about this? Yeah. If we don't have distinct objects, what does that mean? Oh, if we have multiple copies of the same letter in some sense? Well, it's with replacement, so I don't know what that would mean exactly. Like if there were 2 X's in the original bag you're drawing from, oh, then I guess you're saying that you'd have a higher weight chance of drawing those. So right, so these kind of counting problems are foundational, and you can build upon them by having extra things. Like now imagine I'm drawing them where there's more chance that some things come out, and that's going to be kind of the feeling of the second part of the class. So for now, all the balls have identical chance of coming out of the bag, because we're just trying to count how many different combinations there are. Yeah, good question. Yeah. Oh, because this is a typo. Yes, this should be a 1. Sorry. Let's fix it. Okay, so let's fix that. Oops. Okay, thank you, thank you. Okay. Nope. That's not what I wanted. All right. Okay. Now I do want to note. Oh, wrong. Thank you. Oh, I said swap display. All right. How do I do that again? I want to do screen. Hold on. Ugh. I don't even use this view. I don't want it. Okay. Okay. No. Almost there. Okay, swap. Use slideshow. Thank you, Manuel. All right. We also, by the way, okay, so continuing on. So earlier, we defined A as the set of all binary strings with length 7 that contain 2 1s, and we found that that set was size 7, choose 2, just as we did. But we could also have counted the number of ways to draw the positions of zeros. So in other words, we could say that we're talking about this A should be a C should be an A. We could also say we want to know the set of all binary strings with length 7 that contain 5 zeros, right? So you could think about it the other way. Instead of drawing the position of the separators, I'm drawing the positions of the zeros. So we could imagine we're drawing 1, 2, 4, 6, and 7. Okay? Now that's kind of weird because we know that the number of strings is the same. It doesn't matter if we draw the positions of the 1s or the positions of the zeros. So that suggests that from this argument, like if we just counted the other thing, it would be 7, choose 5. But up above, we said it's 7, choose 2. So how can that be? Yeah? Right, they're the same thing. Okay. So in other words, and that makes sense. Randomly picking the positions of the 2 1s is the same as randomly picking the positions of the 5 zeros. If you want, I have a hidden slide that I'm not going to show here because I think it's not worth the energy to show. But you can look at a more algebraic look at why this is true. Anytime you do 7, choose 2, you could also have just as easily said 7, choose 5. Okay? So if you didn't know this, now you know it. All right. So now let's suppose we want to find, we can also think about it this other way, which is, how would this feel if we were picking the positions of the zeros in terms of a general formula? So if we instead chose the position of our zeros, we were to do k prime prime, we're drawing k prime prime zeros. In that particular case, the number of zeros is just going to be k. Okay? 'Cause that's how many things we're drawing from the ball, like from the bag, right? So we had 7 items, then k prime prime is also going to be 7. Okay? So an interpretation of this is that we have k plus n minus 1 total digits, just as before, and we have k of which are not separators. The only thing, I don't think I explained that very well, but the point is that whether I pick n minus 1 on the bottom or k on the bottom doesn't matter. This interpretation is if we're counting the position of the separators, and this is if we're counting the positions of the non-separators. But those are the same thing, right? Has to be. The number of different ways to pick the 1s is the same way as the number of different ways to pick the zeros. Okay? So you'll see both of these versions of this formula in the notes. Now again, the most important part of today's lecture, other than just getting familiar with how these arguments feel, is this notion that counting problem 4 was really just counting problem 3 in disguise. That each multiset can be represented as strings, and then counting the number of strings with these certain properties is actually counting problem 3. Okay? That's the thing that I think you guys are only at 55% correct by the end of that section. So I do want you to think about that again. Why is counting strings unordered sampling without replacement is a piece of homework for everyone to think about after lecture. Unless you voted for that. Then I guess you can just relax. Okay. I should note that there's other names for these counting problems if you want. We could think about this top one as counting sequences without replacement, because a sequence is it's ordered, so we have an ordered sequence of things. Counting problem 2 could be counting sequences with replacement. 3 could be counting sets, so how many different sets are there? And then the 4th is counting multisets with replacement. Okay. All right, any thoughts or questions about that? All right. Okay, I'll give you a little warm-up for Thursday. We're all tired, but let me just give you a flavor of why this stuff is useful. I guess time does permit. And we'll wrap up on this. So as you may know, a plus b squared, you can FOIL that out, and you can get a squared plus 2ab plus b squared. Uh-oh. I think it's worth it. Let's try. Okay. So let's chill and see if we can get through some of this and see if we find something useful. So we can also choose higher exponents than 2, of course. We could, for example, do cubed, in which case we'd get this expression. We could do the 4th, in which case we get this expression. And you may remember that if we wanted to actually look at these, what the weight of each of these terms is, there's the binomial theorem, which looks scary. But basically all it's saying is that this one right here is 4 choose 2, this one's 4 choose 3, and so forth. Okay. So one of the nice things about counting problems is, in addition to being a foundation for probability, they also let us prove certain things in life, like, for example, the binomial theorem. Okay, well, that's a lot of stuff on the slide all at once. So you could prove this using induction, but it would not be fun. But our counting problems give us a straightforward, almost trivial proof. So the basic idea, and sorry that I put all this stuff on the slide at one time, if you multiplied out a plus b to the n, we would end up with 2 to the n monomials. What's a monomial? It's one of these things, a plus b, a squared, b squared. So for example, if we have a plus b cubed, that's just a plus b squared times a plus b, which gives me all these right here. If I do a plus b to the 4th, then I will get this expression. So why are there 2 to the n terms? Someone give me an argument for that? If I'm still holding your attention. So here we had 4 terms. Here we had 8. Why do we have 16 here? Yeah? Yeah, so each time you get 2 copies of the same monomial from before, but now times a and another times b. Okay. So where does the binomial theorem come from? Well, one way to think about it is each one of these factors, so this one there's 4 factors, a plus b, a plus b, a plus b, and a plus b. Each one of them contributes an a or a b to each of these 2 to the n monomials. So if all the factors contribute an a, that's this term right here in purple, which you can't really see super well, maybe on that screen. If all factors but 1 contribute an a, then that's these terms, which are a to the n minus 1 times b. So for example, for a plus b squared, we have 2 terms, which are red. For a plus b to the 3rd, we have 3 terms, which are in red, which are the a squared times b term. Oops, except I did one I'm wrong. Ah, boy. Ah, boy. We're doing so good. It's not good to have to fix a slide when we're in the waning minutes. Okay. 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 All right. Once more. With feeling. Okay. So one way to think about this, and this is just, again, a warm-up for Thursday and a prelude to a piece of the notes that we won't talk about in a lot of detail. The way we could think about it is that, let's say we want to know exactly how many different, say, red monomials there are, or purple monomials, or whatever else. Let's consider an example for, let's say, the 6th power here. So suppose we have a plus b to the 6th, and we want to know how many a squared times b to the 4th terms there are. Well, one of those terms is going to come from where the first 4 contribute a b. Another one are where the last 4 contribute a b, and all other such combinations. So it's like each monomial is going to give either an a or a b. And if we want to know how many monomials there are that have 2 a's and 4 b's, it's basically just saying, among 6 factors, how many combinations are there where we pick exactly 4 b's? How do I do that? Well, that's just 6 choose 4, or 15. Okay, so just generalizing from there, if we think about each monomial as contributing an a or a b, then if we want to know the number of monomials that exist, that have a b to the k, then we just do n choose k. Okay? Because we're just saying how many different ways are that there's k monomials that chose to give us a b. All right. I'm going to call it there. I don't know if it was worth it to do those last 5 minutes. Thank you, everybody. I'll see you Thursday.